So our topic this time around is torsion in circular shafts. Now, when you talk about torsion, you're basically referring to twisting of a circular member. Twisting can happen when you fix a member on one end, then apply a torque on the other. In that case, you may notice that the kind of failure that you may experience can be something like shearing of the member across its section and so forth. So here is our analysis. So we have this shaft. You can consider it to be fixed on this end. Then the torque is applied this side. So we're basically saying here is our fixed end where there is O, then the torque is applied here, meaning going clockwise. So by doing that, basically, you're going to see that the shaft is twisted through angle phi. But again, this is just because you're looking at it from one end. If you decide to look at it from the other end, you'll notice that what you're going to see is a circular object. Oh, sorry, this is perhaps, let me just draw it from here. You're going to see a circular object. Projecting this from your own, you notice it will still mimic that angle there. And you have angle theta here. So this will be your theta. And this is your radius. So this is point A and that is point B. So what you do is that you need to find the length of this arc AB, which is the same AB we have here. So following the principles of what you get when you're using the angle in radians, you just multiply the radius by that angle theta. That gives you the arc length for AB. Now, if you look at this from this other end, from along the length of the pipe, this is approximately equal to this, even if you look at that, because we are still talking about the 2 points, A, B. So in that case, the length of the shaft behaves like your radius, and the angle phi is your angle through which the shaft has been twisted when you look at it along the length. So hence, the two become the same. We're saying R theta is therefore equal to L phi. But what you're seeing here as phi is not just phi, but it's special because it's also representing the, we call it the shear strain. But then if you look at the shear strain, going back to the way we used to understand Young's modulus, we say that this modulus of rigidity is actually shear stress over shear strain represented by phi. So if you make this phi the subject of the formula, you have something like this. Phi, which is the shear strain, will therefore be equal to shear stress over modulus of rigidity. So we can now pick up this equation from here, the last 4 factors, where R theta is equal to L phi, and then you substitute in place of this. So you put shear stress over G in place of phi. So if you do that, then this is what you're going to have. And all you can do now, because we have the first set we want, we can just rearrange them in a standard way. Shear stress over R is equal to G theta over L. Just rearranging them through the usual issues of cross multiplying, divide by this, and then this is it. But then if you consider a strip, a small elemental area, analyze it, you will notice that its length is the circumference of the circle because you're dealing with a circular shaft. And its thickness is dr. So this is what you have. To get the area of this one, you multiply the length by the width. And hence, if you want to get the force acting on the elemental area, we can even call it dF. It's supposed to be equal to dA times shear stress by that small area. Now, one thing you can notice is that What we are calling a small area is a product of this and that. So then you can then rearrange it that therefore it should be shear stress by 2 pi r multiplied by the width. 2 pi r is our length. Multiply that by the width, which is the r, the thickness. This representing the width, just this one. So this is what we've written here. The whole of this is representing the force. But if I'm talking about the torque, I have to multiply that force by the radius. Force times radius gives me the torque. So I have this force times that radius. So once I do this, then I have that. Because what I'm going to do now is to multiply this r by that one. Not very long, just a while ago, we were just from rearranging this equation. And you can already see the shear stress here. So make shear stress the subject of the formula. This is what you have. You have shear stress is equal to G theta R over L. So let's substitute where the shear stress in this expression, we put this same expression, G theta R over L. So once you do that, there's R and there's R squared. You have R cubed. The rest of the constants will be outside there. They will remain the same. There's G theta over L and there's also 2 pi. Then you can now integrate. When you're integrating R cubed, what you have is R raised to power 3 plus 1. Then over the same 3 plus 1. Which gives us the result like this. R raised to power 4 over 4. But you can see there's a 4 here and there's a 2 there. So 2 into 2, 1. 2 into 4 is a 2. So hence you have pi r4 over 2. Now let's get this clear. Our J, which is the polar moment of inertia, is equal to what we have here. Pi r4 over 2. Pi r raised to power 4 over 2. If you substitute for d over 2 here, what you're going to have is pi d4 over 32. So then you substitute there d over 2 in place of r, you have that by d4 over 32, which is just this one. But again, we're just saying that this is representing J. So let's take it back to the equation and replace J in place of all this. So you have G theta J over L equals T. If you check back our equation that we already had G theta over L. So we just need to get rid of this one. So we'll say divide through by J. You have T over J is equal to G theta over L is equal to shear stress over R. So then T over J is equal to G theta over L is equal to 2 shear stress over D. Let's look at some examples then. The first example, we have a shaft whose length is 2 meters required to transmit 100 kilowatts of power when running at a speed of 800 RPM, twist angle 1.5 degrees, and the shear stress 90 newtons per square millimeter. Then we need to find the torque, diameter of the shaft, also the diameter, given that modulus of rigidity G rather is 200 gigapascals. Information provided, power 100 kilowatts. Convert kilowatts to the normal, which is the watt. You have 100,000 because you multiply that by 1,000. Rotational speed 800 RPM. Twist angle 1.5, but you cannot use the degrees because the angle that we're using from our analysis is in radians. So we multiply that by pi over 180 in order to convert to radians from the degrees. Shear stress is 90 megapascals. So 90 megapascals meaning 90 times 10 power 6. In fact, here what we've been given is per square millimeter. When you convert from square millimeter to square meter, it means this number which is below will end up going up there. It's 1,000 squared. We divide by 1,000 squared, meaning we end up multiplying by that. So in the end, it's as good as 90 times 10 raised to the power 6. The length of the shaft we've been told is 2 meters. So with this information, we have all the details that we're looking for or that we have been provided with. Let's get now to power. We know power, what we've been given with the information provided. To get power, we'll say 2 pi nt over 60. So make t the subject. You have power times 60 divided by 2 pi n. So power is 100,000, 60 is there. Then you have 2 pi times n, which is 800. So then your answer is 1193.662. Again, power is 2 pi nt over 60. If you make t the subject, you have power times 60 divided by 2 pi n. Then all you do is just substitute from here, and you have your answer here. Next, we're looking for the torque, rather the same diameter, but given other conditions, because we now need just to find the diameter because we've already been given the torque. So here, I decided first of all to make use of R. So here, I already have my R, which is that. So when I say T over shear stress is equal to, here first I have T over J is equal to shear stress over R. If I rearrange, it becomes J over R is equal to T over shear stress. Meaning that all I want is the R's to sort themselves out. So these will cancel, then I'll have pi R cubed over 2. Now here, if I want, at this point, I can have something like this. I can have T over shear stress is equal to, then I go ahead and plant pi, this is my pi d4 over 32. This one I've written is basically just representing J. Then I'm saying multiply everything by what? By not 1 over R, not 1 over R, but 2 over D. 2 over D. Where is this D coming from? Because I know that R is D over 2. D over 2. Because the D is here, meaning the 2 is on top. When you do that, what you have now will look like this. If I just simplify what is here, I'll have pi D cubed. Why D cubed? Because this D and that D power 4 will cancel. Then here we'll have power 3, whereas the other one will dissolve. So this will be pi D cubed over 16. Because here, 1, here I cancel, I have 16. 2 into 32, that is 16. So then, what am I having now? Here I can now say that my T over shear stress is equal to pi D cubed over 16. Meaning that here, if I decide to make D the subject of the formula, it will still be this D. Instead of having 16 there, I will simply say my D will be equal to cube root of this 16 by T. So I'll have 16T. So it will be 16T, everything divided by, so 16T over pi. And remember, there's already shear stress. This is what I'll have. Instead of 2T, over pi shear stress. I can have 16T over pi shear stress. Results, same. If you substitute here, and if you go ahead like we are doing here, you get the same thing. In our case here, I say R is equal to 2 times that, which is the torque, divided by pi times the shear stress, which is 90 by 10 power 6, and my R is this. Now, because in my case I was using radius, I need to take a further step by multiplying this by 2. So D is 2 times R. So 2 times the answer I found, which gives me 0.0407. It is basically the same result. Condition, we've been given what if you have that. So here again, instead of shear stress over R, I can say 2 shear stress over D. It's the same thing. So here, R is equal to shear stress L over G theta. And here again, I've just decided now to use D. So that D is equal to 2 shear stress over G theta. Because here it's like I'm already having D over 2 instead of R. So all I do is just cross multiply there, and we're good to go. So D is 2 shear stress L over R, meaning 2 there. Shear stress is 90 times 10 power 6. The length, this length is 2 meters. Then G is 200 by 10 power 9. Theta is 0.02618. My answer is 68.75 millimeters. 0.06875 meters. That is how you find the diameter with information provided in that manner. Now, look at the second example. In the second example, you have shaft thickness 10 millimeters, external diameter 60 millimeters, length 1.5 meters, modulus of rigidity 100 kilonewtons per square meter, and the twist angle not to exceed 1 degree. Then we need to determine the torque, power, just those two. But then my main issue is here, G. Where is our G? In this case, it's here. Yes, written here. If you look at this value for G, first of all, we've been told that the G is 100 kilo. If I convert kilonewtons to newtons, I say times 10 power 3. So this is times 10 raised to power 3, which is like 1,000. Then converting Newton per square millimeter, meaning converting these square millimeters to square meters. This is per square millimeter. So meaning that the converting factor for this should come on top, which is 1,000 squared, or basically 10 power 6. Then we've converted to square meters. So when you bring these two together, they are having the same power, which is the same base, which is 10. 6 plus 3 gives me that 9. So that's why I have now 100 times 10 power 9 pascals. Theta, I've been told it's 1 degree. So 1 times pi over 180. All I'm doing here is convert from degrees to radians. So 1 by pi over 180, which gives me simply pi over 180, or 0.01745 radians. That's the information. But then there is this other item we have left hanging. The thickness of the shaft is this. In other words, the shaft will have an external diameter of 60 millimeters, but then we also have the thickness, meaning that this is a hollow shaft. In the middle, there is no material. The thickness we've been told is 10 millimeters, meaning that even below here, what I have below here is also 10 millimeters. If this is 60, then I have 10 here and another 10 millimeter here. How do I find now what is in the middle? I just subtract this 60 minus these two 10s. So first, let me total up. 10 plus 10 is 20. So 60 minus 20 will give me this. This is the 40. Basically, I always say that there's this, which we always use, where we say D, the outside diameter, minus twice that thickness of the shaft. So in this case, my external diameter was 60 millimeters minus then twice or 2 times the thickness, which is 10. Now, once we've done that, it gives us the 20. So that's how come now 60 minus 20, you have the 40 there. So that is our internal diameter. And the next thing you do is just to make sure that everything is converted now to meters. 60 millimeters converted to meters. Divide this by 1,000. So divide that by 1,000. By 1,000. You do the same for this other one also. Divide it also by the same 1,000. So with the first one, you have 0.06. The second one, which is 40, you have 0.04. So 0.06 raised to power 4 minus 0.04 raised to power 4. And your answer is going to be 1.021 times 10 raised to power negative 6. Now, this is our J. So having found the value for J, means you've now completed the pieces of data that you were looking for. So making T the subject of the formula from here, because the torque is what you're looking for, is T is equal to the same G theta, but there's also going to be like this. It will be G theta, G theta, J. G theta, J over L. G theta J over L. Give my handwriting, it's not a power, it's basically just a factor. It's on there. So G theta J over L. So T is what you're looking for. G is 100 by 10 power 9. Theta is pi over 180. Pi over 180. J is 1.021 times 10 power negative 6. L, which is the length of this shaft, is 1.5. Then that gives us our T. And that's our answer, 1188.008, which is basically like 1188. Then you can go ahead and find your power. 2 pi nt over 60, meaning 2 pi n by that over 60. And your answer is therefore 62. 203.95 watts. So thank you very much. We've come to the end of this one. Again, you have your exercise there with some answers already planted for you to make sure that as you are working out, you can see where you need to make corrections here and there. Again, thank you for the comments I've been receiving. We are constantly making sure that we acknowledge, and where we have typos, we take care of them. That's how we refine most of the documents. Thank you, and we meet in our next lesson.